Well, Professor Clements with you again as we talk about electromagnetic waves. In this video, talking about the intensity of the wave, the power passing through a certain area. Our electromagnetic wave we're going to discuss here is a radio station, 55,000 watts, expanding out in all directions. That means it's going to be expanding out into a sphere. So if I have the radio tower perhaps here and the antenna here, we'd have the energy expanding out three-dimensionally in all directions into a sphere. As the wave moves outward, we can calculate the intensity of the wave based on the power divided by the area that power is spread out over. And for this situation, expanding out into a sphere, we're going to have that power over an area of 4 pi r squared. That's the formula for the surface area of a sphere. R is the radius, so 4 pi r squared. So in our situation here, we're given the power, 55,000 watts, and we're given the radius. We're going to let that power pass through an area here that's 15 kilometers away. So 4 pi and then 15 times 10 to the third meters, and that has to be squared, r squared. We have to convert from kilometers into meters and do this square calculation. So when I did that, and you should perhaps pause here and do this yourself, I found an intensity of 1.945 times 10 to the minus 5 watts per square meter. The power drops dramatically as the radius increases. The intensity drops dramatically. The intensity is inversely proportional to the square of the radius of our circle, of our sphere. So we come up with this number. Then how much power is passing through 0.6 meters squared? Well, we have meters squared in the denominator here. So the power passing through 0.6 square meters is going to be 1.945 times 10 to the minus 5 watts for a full square meter times 0.6 square meters. And on my calculator, that produced 1.17 times 10 to the minus 5 watts. That's how much power passes through this 0.6 meter squared, perhaps receiving area. Now let's move out a little bit. Same radio station, same power, and now we're 30 kilometers away from the transmitter with the same receiving area, 0.6 square meters. So what happens now when we've increased this distance? Well, notice that we've increased the distance. We went from 15 kilometers to 30 kilometers. Notice also that the intensity is proportional 1 over r squared. If we just eliminate all the constants up here, we're changing r in this second problem, and the intensity is inversely proportional to the square of the radius. So we've doubled r. That's going to be a factor of 4, a new factor of 4 in the denominator if we would do this calculation. So I is going to be less by a factor of 4. We're using the same area that we had up here, but this number is going to be 4 times smaller. So I am simply going to take 1.17 times 10 to the minus 5 watts and divide by this proportionality factor, kind of scaling factor. We're twice as far away. The intensity gets smaller by a factor of 4. 4 is 2 squared. And you may want to do the calculation in detail, put in 30 times 10 to the third meters here and find the intensity and then multiply by 0.6. But hopefully you'll come up with the same result that I came up on my calculator at this point. I have 2.92 times 10 to the minus 6. So the power is smaller now. As we're further away, we've doubled the distance. The power's smaller by a factor of 4. And then this last problem, Suppose we have a laser. A laser is notable in that the light coming out of the laser does not expand out into a sphere. It keeps more or less a beam. We won't worry that that beam spreads out just a little bit. But let's calculate the intensity. And again, intensity is power over area. For the situation where this 0.5 milliwatt laser has its light spread out on a spot that has a diameter of 0.8 millimeters, well, we're given the power. I do need to make this into standard units, so the milli gets replaced with 10 to the minus 3. The area here is a spot. Let's say it's a circle. That area is pi r squared, so we'd have 0.4. We're given diameter. We have to make radius, and the milli creates a factor of 10 to the minus 3, and then pi r squared. Don't forget the squared operation. So you may want to pause here and do your own calculation. I have 9.95 times 10 to the second power watts per square meter, or 995 watts per square meter. And lasers can be more intense because their power stays in a smaller area, stays in a beam. You should never point a laser at someone's eye, or you should not yourself look into the beam of a laser unless you're having some medical procedure under the control of a qualified person running the laser. Lasers are hazardous. Even though this is not a powerful laser, good safety practice, don't look into the beam of a laser. This is just a calculation that would give you a feeling here. 1,000 watts per meter squared. 100 watt light bulb, 10 100 watt light bulbs would be 1,000 watts. So that's not going to be comfortable. So keep practicing and ask your instructor questions.